Hi guys, and welcome back to Elevate Chem. I'm Jesse with another concept video. Now this is our third video in our 5-part series looking at stoichiometry and is really designed to tackle those questions that have a lot of elements going on. Now, as always, we're going to be looking at an exam style question to really test that understanding, because ultimately the best way of doing that is by looking at an actual exam, because that's what you're going to need to do. Now, the first thing I want you to do is to have a go at this question, and this is from the VCE 2014 chemistry exam, and it's question 8. So download this practice paper, pause the video, and I'll see you once you're done. Fantastic. Now again, as with most stoichiometry questions, I find there is a lot of text here, and I think that is one of the easiest ways to muck up, is by getting overwhelmed with the amount of text. So I'm going to jump right into it and show you the method which I would use to tackle this question. So the first thing I would do is actually skip this starting text, because I want to see what I need to know first. So A, what type of reaction is this? Okay, so all I need to really understand is the equation in front of me. I'm going to put a little asterisk next to that. And looking at it, I can see that I have some electrons on the right hand side of the equation, and that means if I'm losing electrons from my reactants, that means I have an oxidation reactant. Oxidation reaction. Now the examiners were actually really generous this year and also gave out marks for redox. However, I highly recommend you specify whether or not it's reduction or oxidation, as I doubt they'll be that generous every year. So part B, here's where the text comes in, guys. A lot of text going on there, and again, I'm not sure what I need yet, so I'm actually going to jump down to I and see what I need to understand. Determine the percentage by mass of SO2 in the apricot sample. Okay, cool. So I can see that I've got SO2 going on here. I'm given a molar mass. And then looking through the rest of the question, I've got barium sulfate after a reaction, how much mass is added. I've got an equation here. It doesn't involve SO2, and I'm starting to get potentially a little bit worried. Now it's time to read the question. Guys, if you don't have all of the numbers you require sitting next to you, the element or the molecule that you're after, it's time to read the question and really understand it here. I'm going to read through this really quickly. Sulfur dioxide is often used as a preservative in food and drink. Okay, I don't care about that. That's just sort of a fun fact of the day. The sulfur dioxide content in dried apricots was determined by gravimetric analysis as follows. Okay, so I have some ideas in my head. Cool, we are looking for sulfur dioxide. Excellent. We're looking in dried apricots. Sure, pretty tasty. And they're determined by gravimetric analysis. Okay, that must be what this is all about here. Because I am weighing things, it must be a gravimetric analysis. The dried apricots were powderized in a blender. Awesome. A sample of the apricot powder weighing 50 grams was put into a conical flask containing 100 ml of deionized water. I still haven't read anything about my sulfur dioxide yet, so I'm going to keep reading. A 3% solution of hydrogen peroxide was added to convert the dissolved sulfur dioxide, there is our guy, to sulfate ions. Okay, that's probably pretty important. Next part of the question, an excess of barium chloride solution was then added. The barium sulfate precipitated was filtered off, dried, and weighed to constant mass. Okay, now I understand the picture here. So, let's work backwards. Starting with this last sentence, the barium sulfate precipitate was filtered off, dried, and weighed to constant mass. That's what this highlighted step is down here, guys. This is the precipitate from that gravimetric analysis. The most important dot point, though, at least for this question, was this third one right here. It states that sulfur dioxide is converted to sulfate ions. And it didn't actually state here, but I'm going to assume that A, this is 100% efficient, and B, it's a 1-to-1 reaction. Doesn't state that anywhere, but I'm going to have to work on that, because otherwise we don't have anything to go off. And you know what? That was the correct solution for this exam question. That was what you were meant to do. So I'm going to get stuck right into it. And how we're going to determine the percentage by mass? Well, that means we're going to need a mass ultimately. If we need a mass, that means we're going to need the moles. And the only way we can get the moles is by using molar ratios. We can see here that this is the only reaction that I'm given. And it states that there is a 1-to-1 ratio between my barium sulfate and my sulfate ions. And again, we're assuming from this part of the question that my sulfate ions, or my moles of SO4 2- is equal to my moles of SO2. And I'm going to assume that's correct because I don't have anything else to go off. If you get into a situation where you have this gut instinct that you have to assume a statement like this, guys, do. But this wasn't completely out of thin air. It's because of that third dot point that I highlighted. That's why I'm making this assumption. Awesome. So I'm going to get stuck into it. So firstly, I'm going to need the moles of barium sulfate because that's the only thing that I have a starting mass for. So moles of barium sulfate is equal to mass divided by molar mass. Now my mass is my change in mass here. I've got my dry filter paper, and then I've got my, I'll draw out a little sketch. I've got my dry filter paper, and then I've got my dry filter paper with all my barium sulfate on there. And the difference between these masses, guys, that's the mass of the barium sulfate itself. So that means my mass is 1.338 minus 0.864, and dividing by my molar mass, 233.4, and that gives me a value of the moles of barium sulfate is 2.03 by 10 to the minus 3 moles. Awesome. Now, the moles of barium sulfate, from the equation itself, from this chemical reaction right here, we can see that that is equal to the moles of SO4 2 minus. And then from this assumption here, based on that third dot point, I'm going to say that that is equal to the moles of SO2. Now the actual solution skipped that intermediary step of saying it was equal to the moles of sulfate. However, almost just for my own sake, I want to write that in so I'm sure that I'm understanding everything that's going on. I never really feel comfortable just answering a question the way that I feel is right, unless I know that I'm understanding each of the steps that I'm taking. So I'm going to write down that this is equal to my 2.03 by 10 to the minus 3 moles. And now I need a mass, because the question is asking for determine the percentage by mass. So my mass of SO2 is equal to moles times molar mass, which is my 2.03 by 10 to the minus 3 times 64.1, and that gives me a value of 0.130 grams. Notice I'm using 3 significant figures here. It doesn't actually matter until I get to the end that I use 3 significant figures, but I'm going to stick with that for now. Now I need to get into percentage. So percentage mass to mass of SO2 is equal to the mass of my sulfur dioxide, which is 0.130, divide by, well, now I need to divide by, well, where was all this sulfur dioxide coming from? Well, if we read the question here, it says sulfur dioxide is often used as preservative. The sulfur dioxide content in dried apricots. So there was 0.130 grams of sulfur dioxide, and that was from 50 grams of the dried apricots. So I'm going to divide that by 50.00. And then it needs as a percentage, so simply multiply that by 100, and that will give me the final value of 0.260%. Awesome, fantastic. Moving on to II. Now again, this was a question that threw off a lot of students, and the reason why is this little word or symbol, however you want to describe it, right at the end there, ppm. ppm stands for parts per million. And I'm sure you're aware of the fact that that's what it stands for, but what does that in practice mean? Well, in a very literal sense, it does mean parts per million. But how can I sort of represent that? Well, in this case, we're talking about mass, so I'm going to deal with mass. The reason why I know I'm dealing with mass, the previous question was discussing mass. We worked out a percentage of mass, and ultimately we were looking at the mass of an original sample and how much of that was a particular chemical species. So I'm going to again assume, based on that logic, that this is mass. So, parts per million. What that means is how many grams of, in this case sulfate, is present in 1,000,000 grams of substance. And that's as simple as it gets, guys. And if this was liquid, of course, that could be mils per million mils. And if I wanted to, I could convert the 10 to the 6 grams in tons, but it really doesn't matter. And I find it simpler to look at this perspective. So ultimately, it's a ratio. And I find the easiest way of working out this question is by working out, instead of this, I work out how many grams are in 1 gram. And then I simply multiply that value by 10 to the 6. And that's the easiest way, I think, to work it out. So I'm going to work out how many grams are in 1 gram. Well, I know that I have 0.13 grams in 50 grams. So that means mass SO2 in 1 gram equals 0.13 divided by my 50, and that gives me a 2.6 by 10 to the minus 3. And again, the reason why I'm doing this is to actually calculate the amount of mass in 1 gram, because then all I need to do is mass of sulfur dioxide in 10 to the 6 grams equals 2.6 by 10 to the minus 3 times by that conversion factor that I've got there, by 10 to the 6, and that gives me 2.6 by 10 to the 3 ppm. And the reason why it's parts per million is it's my mass of sulfur dioxide in 10 to the 6 grams. So I've got 2.6 by 10 to the 3 ppm. And again, this is a mass to mass basis. So moving on to II. Why were the apricots ground to a fine powder prior to the reaction? It did state in the question that that is what occurred. If you wanted to, you could go up and read that. But really this comes down to understanding. Why would I want to do that? Well, one of the key reasons is to speed up reaction. And well, what was the reaction? In this case, release of SO2, of that sulfur dioxide. And another reason that you could write down is ensure all SO2 is available for reaction. Both of those answers were acceptable this year. To be specific though, it was stating this release of SO2, and you wouldn't have gotten a mark if you simply said speed up reaction, because they wanted you to be specific and say what sort of reaction was occurring here, what specifically was being sped up. Alright, jumping down to CI. Again, I'm going to skip this text for now. I might need it later, but right now I'm going to see what I need for this question. What is the mole ratio between iodine and water in this reaction? So I'm going to assume it's this reaction right here. Pretty safe bet. Pretty straightforward question, guys. Hopefully you didn't have too much trouble with this one. And if you did, that's fine. All we're looking at is what is the mole ratio between iodine and water. Water is 1, iodine is 1. It's a 1-to-1 ratio. Some students wrote down that it was a 1-to-2 because they were comparing the number of individual atoms of iodide. However, iodine is actually the substance I2 itself. So it's simply a 1-to-1 reaction. You didn't have to overthink this one or overanalyze it. Just see that there is a, of course, invisible, but 1 there and a 1 there, so it's a 1-to-1 reaction. Awesome. Jumping on to the next part of the question. Again, I'm going to be skipping this text for now. See what I need later. Determine the mass of water present in a 10 ml sample of oil. Okay, cool. So now we're definitely going to have to start using some of those equations that we've got there and some of those values. So determine the mass of water present. Well, I've got the molecular weight of water. So that means ultimately I'm going to need moles of water. And I know that I've got a 1-to-1 ratio between iodine and water. So most likely I'm going to need to work out the moles of iodine so that it's equal to the moles of water, and then simply multiply it by the molar mass. And in this case, that is exactly what I had to do. So it states here that the iodine titrating agent was prepared by dissolving 15 grams of iodine in methanol using a volumetric flask and making up the volume to 500 mils. A 10 ml sample of oil was analysed using the iodine solution. The mean titer was found to be 4.95 mils. Awesome. So there's my 10 ml sample of oil. So I'm determining the mass of water present within this bit right here. And it states that the titer was found to be 4.95 mils. However, I know nothing about this titer, at least not yet. I don't know its concentration, so I can't quickly work out how many moles of iodine is actually present within that titer. Instead, I have to go back to the original solution that was constructed. Because essentially what happened here, guys, was I made a big batch of iodine solution. I made 500 mils of it, and then I took out a small portion of that, 4.95 mils, and that was the amount of moles present within here. So I'm going to have to determine the moles within this large sample, and then work out, well, how many moles would be within 4.95 mils of that solution. So, my moles of I2 in my large solution I can find given this 15 grams. So is equal to mass divided by molar mass. So 15.0 divided by 253.8. And that gives me a value of 0.0591 moles. And keep in mind, guys, that's the moles in this 500 mils. So the moles of I2 in the titer is equal to my 0.0591. So that's my moles in 500 mils. So what I'm going to do is I'm going to multiply this by this little factor. And the factor that I'm going to use is divide by 500, but I'm timesing it by 4.95. So what I'm doing here is, because this is the value present within 500 mils, I'm going to divide by 500, and that's essentially going to give me the moles per mil. And then I'm going to multiply that by 4.95 to get me the moles per 4.95 mil, which is the size of our titer. And that comes out to a value of 5.85 by 10 to the minus 4 moles in that titer. So we know from this question up here that it's a 1-to-1 ratio, and it was this titer that was reacting with the 10 mil sample. So therefore, moles of H2O is equal to moles of I2 titer equals 5.85 by 10 to the minus 4 moles. And to get the mass of H2O equals moles times molar mass equals 5.85 by 10 to the minus 4 times 18.0 equals 0.0105 grams. And if you wanted to, you could also write that as 10.5 milligrams. They're both the same thing. I've written them both to three significant figures because that was my least accurate piece of data, and that was what there was to the question. Alright, moving on to I. Determine the percentage by mass of water present if the density of the oil sample is 0.918 grams per mil. Now, I'll give you a bit of a tip here, guys. If they give you some pretty odd value, like a density, 9 times out of 10, you are going to need to use it. Especially if, like in this example, it's just one extra piece of data. If you're given a question like this, when there's a lot of stuff going on, you might not need everything. But usually if they've given you one extra fact or one extra value, you're usually going to have to use it. So we want to determine the percentage by mass. And that means what I need is mass of water. And it's looking for determine the percentage by mass of water present in the oil sample. So we're going to need to divide that by the mass of the oil. Well, we already know the mass of the water because we found that in the previous question. And the mass of the water is equal to 0.0105. So now I need to divide by my mass of oil. So mass of oil. Well, usually what we would use is moles and times by molar mass. But if we have a look at this question, we don't have either the moles of oil or the molar mass of the molar mass of the oil. So what we're going to have to use instead is a different value here. And that's why they've given us the density. So the density, sometimes you'll see it written with this symbol, which is called rho. Sometimes you'll see it written as a D. In VCE, most of you guys are probably going to be used to using a D. It might be different in other states. So the mass is equal to the density times the volume. And the reason why I know this, in fact, I might not necessarily know this equation, but instead I can use what I've talked about in a couple of other episodes of dimensional analysis. A couple of fancy words, but really what it boils down to, guys, is if I want mass, that's going to be in grams. And if I look at my density, I've got grams per mil. And what do I need to multiply that by in order to be left with just grams? Well, if I multiply it by mils, these mils are going to cancel out and I'm going to be left with grams. So that means my density needs to be in grams per mil, which it is, it's given to me. And that means the volume I need to use has to be in mils. So putting those numbers in, 0.918 times, how many mils of oil was there? What states in the question? It was a 10 mil sample of oil. So I'm going to simply multiply that by 10, and that gives me a mass of oil of 9.18 grams. So now I'm going to continue the working down here, guys. You should do it on those written lines. But the mass of H2O divided by the mass of oil, I substitute in that mass of oil of 9.18, and that gives me a value of 0.115%. And that's the percentage by mass of water given that density. Alrighty, so that was certainly a pretty decent sized question here. So let's break it down and see the bits that were important. So one big thing about this question is considering the amount of multiple pieces of data. There was a lot of values being thrown around and you need to work out what was important. And a key element a couple of times was actually the units. Coming down here, parts per million. Further down, we had density using dimensional analysis. Those were some key things we needed to be able to use. Ratios were also critical, as I used in parts per million. There were other ways of doing this question. Don't be stressed if you did something different. But using ratios and understanding that there was 0.13 grams in 50 grams, therefore you could find the amount in a million grams. Being able to use those sorts of ratios is really important. Finding that it was an oxidation reaction should have been reasonably straightforward. Oxidation is lost, something you're just going to have to lock into your brain. Moving on here, reading through the question, not right off the bat because I find that pretty confusing, but reading the actual what do you have to do first, and then identifying the key elements within the question that you're actually going to have to use to answer it. Key understanding here, guys. Other steps, including down here, again, was ignoring this text originally and then working out what elements you needed to understand. Because there were large portions of this question that I didn't need to read at all. This whole paragraph here I did not read because it wasn't useful to me. It gave me some background information, which sure might be useful in increasing our understanding, but in an exam type situation, really what I'm only interested in, guys, is stuff that will help me answer the question. Fantastic, guys. Look forward to seeing you in the next episode.